Okay guys, let's try to do the second example. So here we're trying to find the particular solution to this differential equation. Just a reminder, it's a differential equation because it involves a derivative. When it says particular, that just means that we're going to find the c here. We're going to use this point to do that. I think you guys have been a little bit familiar with this before. So we're just going to take the integral of both sides. So the integral of dy dx is just y. The integral of e to the x is e to the x, and then the integral of minus 6x squared, you add 1 to the power, divided by the new power. And then we need that plus c. So here, because we're given a point, we're able to find the c and pin down the function. So before, in the last example, we had some function that could have been some vertical translation of each other based on what the value of c was. But here we're told that we have the point 1, 0. So we now know that our function, whatever it might be shaped like, has to go through that point. So it tells us, pins it down. All right, so we're going to plug in this point 0 for y, and e to the 1 minus 2 times 1 cubed plus c. If you solve this for c, you're just going to get 2 minus e. I know that's not pretty, but it is a number. Oh, I have two equal signs. So that equals c. So then you go to write your final equation, and you get y equals e to the x minus 2x squared plus the value of c that you found. And that's how you write your final equation. That's it. So now the third example has to deal with when we go to solve a differential equation, but there is a discontinuity in our solution. So anytime there's an asymptote or square root that could have a negative, or a fraction where the denominator could be 0, there's a potential for a discontinuity. But we start this the same way. We're going to integrate both sides. So the integral of dy dx is just y. The integral of 2x is x squared, and the integral of secant squared is tangent plus c. So the reason why this has a discontinuity is because of this tangent piece. And that's the only part of that could potentially restrict the domain from being all real numbers. But before we deal with that, let's find the c. So we're going to plug the 3 in for y, the 0 in for x, and then find the c. So 0 squared is 0, tangent of 0 is 0. Hopefully you remember that. So c is just 3. So you get y equals x squared minus the tangent of x plus 3. So because we have this tangent in the equation, that's going to provide some issues with our domain. So if you kind of think about, this is the only part that's going to cause problems with this, so I'm just going to think about the graph of tangent. So if you think about tangent, it has asymptotes at negative pi over 2, pi over 2, 3 pi over 2, and so on. So we need our solution to a differential equation to represent a continuous function, because our derivative must be continuous if it's going to be differentiable. So differentiability implies continuity, therefore this must be continuous. So it's not naturally continuous, so I'm going to restrict the domain in a way to make it continuous. So we're going to say that this function exists on this domain from negative pi over 2 to pi over 2. I chose this piece of it because that's where the initial condition lied. 0 was between negative pi over 2 and pi over 2, so this must be where I was. Let's say I had an initial condition that was pi comma 5 or something. Well, then I would have been in this piece, and my domain would have been from pi over 2 to 3 pi over 2. It depends on, you have to restrict your domain based on this initial condition. So the biggest mistake that people make on this on the upcoming test is that they just say that the domain is that x cannot be negative pi over 2 or pi over 2 and so on. That's not the point of restricting the domain. The point of restricting the domain is to force this function to be continuous. It's not just to list the problem areas. So in doing that, then you're making this be a continuous function. Okay, one more example. So this, there's also, this is the last example, like the last homework before it gets to the slope fields one. It's number 23. So number 23 uses this concept on your homework. So sometimes you have to use the fundamental theorem of calculus to solve a differential equation if you can't like find the antiderivative. So here I have some derivative equals some function, and I want to find the original. That's like all the other ones we've been doing. The problem is with this one is that when I go to take the integral of both sides, yeah, the integral of f prime of x, that's just f of x. But there's no antiderivative of e to the negative x squared. There's no like way to, you know, to like perform this operation of taking the integral of this. So there's just no function who has e to the negative x squared as its derivative. There's lots of functions out there that don't have an integral. So you have to just write it explicitly. You have to leave it as involving an integral. So like with all functions that we had that involved an integral, we had to put this like dummy variable in. This way x isn't representing like too many things. And it's most convenient to put the x in the top piece of this. It's not the only way to do it, but it's the most convenient, most straightforward way to do it. So now what I'm doing with this is I'm trying to create a function that meets two requirements. That when I take the derivative of it, I get the original back. I want it to be so that f prime of x is e to the negative x squared. So in order to do that, I need to use the fundamental theorem of calculus because this is defined by an integral. So in order to take the derivative of an integral, the bottom bound, and use the fundamental theorem, the bottom bound needs to be a constant. Doesn't really matter which constant it is. This is not the best choice, but I'm just going to pick a random one for now and then show you like how to pick a better one. So if you let 0 be the bottom bound, then it does meet this requirement. When I go to take the derivative of this, bottom bound's a constant, top bound's x, and then I can just like fill in this x here, and I get this. So now it has met this requirement, but it doesn't meet my initial condition. I need it to be such that when I plug 7 into this, I get 3. Well, right now, if I like plugged 7 into it, it would be difficult to evaluate without a calculator. So like you would need to figure out the area under this curve from 0 to 7. That's not obvious what that is. So maybe we should not pick 0. Maybe we should pick a different number as a constant. It didn't matter which constant we picked as long as it's a constant. Maybe we should pick one that makes it convenient to plug in 7. Hopefully you realize that that's 7. If I make this bottom bound be 7, then when I go to plug 7 in for x, this piece of it will just be 0. I know you don't want it to be 0, we want it to be 3, but at least we know what it is. It's easy to calculate. Then we can kind of cheat here, and like it's kind of cheap, but if I want this thing to equal 3, well, let's just add 3. And now when I plug 0 into this, I get 3, because the integral from 7 to 7 is 0, and then plus 3. So this is the solution to this differential equation. I know it seems strange that it involves an integral. It seems like we don't really do any work, but it does meet the requirements. The two requirements are that when I take the derivative of this, I get this equation back, and when I plug in 7, I get 3. So to kind of give you an analogy of like why this is acceptable, like let's say, totally separate, like let's say I was taking the sine inverse of 1/2. That's asking me the sine of what angle is a half, and hopefully you know that it's pi over 6. So I like simplified this. I like performed this operation to 1/2, and I was able to simplify it to pi over 6. But like there's some angles that you plug that in and you just don't know what that is. Like for example, if I wanted to do the sine inverse of 0.8, we don't know what the sine inverse of 0.8 is in our heads, but you can still write it like that. Like that's still a number. It's not a pretty number, but it is a number. Kind of like this isn't a pretty function, but it is a function that meets the requirements that it wants us to meet. The other